my name is Jian, and I'm a third-year PhD student from Queen University of London, and my supervisor is Sean. So today I'm just going to explore one simple and interactive problem about whether instance-specific menu prompt is necessary for promptable segmentation. So what is promptable segmentation? Actually, it has been pretty popular, even it has been proposed for maybe decades. Because last year, segment anything model has been proposed. We know it has a very, very strong generalization ability. And this kind of generalization ability is not a magic. That's due to it has been trained on a very large scale prompt mask pairs. For getting its prompt mask pair, Meta has just provided for each image, they have a prompt and a mask, but they do not provide instance-specific annotation about what exactly it segments or what exactly this mask refers to. So in this case, even though it can get a very strong generalization ability, for example, maybe we give an image, we just point at something, it can make a very, seems like pretty well prediction. But actually, it do not exactly know what it predict. It have a very strong mask prediction ability, but do not have very strong label prediction ability. So for compensate that, they have to provide a menu instance-specific prompt, even though this image is very simple. For example, there's a wall, and here is just one simple lady just stand on here. All of us know we want to segment it, but if we do not provide any prompt, it cannot be achieved by SAM. So our problem is very interesting and straightforward. Can we just get rid of this menu instance-specific prompt? Can make it apply to the real-world application? You know, if we apply SAM in recommendation system, this will be 1,000 or maybe billions data for us to do. But in this case, if we provide instance-specific prompt for each image, it's not realistic. So here we do exploration on a very intuitive pre-experience. Here the orange is that we provide each image from the camel dataset, which is from a camouflage animal detection dataset, that we provide a point or private Scrabble. Both of things we just get randomly from the mask ground truth. So first thing is that we provide point 1 and point 2. Both of them refers to the same object. We make a slight difference on it. We can see we use that MAE as the final metric. The lower is better. So basically, the points itself can be a little bit random. Even if the point can be a slight different, the result can be different. A straightforward idea is Scrabble provides much more thing than the points. If we provide Scrabble a thing, the performance should be better, but actually the result is undercomposed. That's because people and the SAM model have some bias between the understanding. Sometimes from people's side, the Scrabble itself is on the mask, so it has clearly for people to understand, here's the thing we want to segment. But for the model, they do not understand this. So the performance becomes worse. So the blue thing is that we want to do our proposed new setting, which is called menu-free text generic prompt setting. In this case, for all image within the same task, we want to know if we just provide a task description as the task generic prompt and feed this only task generic prompt straightforward to the model, whether it can do pretty well. We know SAM now cannot be straightforward to transfer the vocabulary into the SAM itself. So we borrow a model called clip surgery. Clip surgery is very simple. It's trying to utilize attention map to transfer the vocabulary into point or heat map. And then we just select the threshold has been proposed by its authors to transform into high confident positive prompt and a negative, high positive negative prompt and fit them both into the SAM to see whether the result can be good. And you can see here, the clip surgery at the SAM model can really work, but it gets worse problems. So you can see its pipelines can really work, but in some promotions. Why it causes problem? So in next page, we do more exploration with much more image to explore our motivation. Here is two images from camouflage animal detection. Here is a snake, here is a grasshopper. Both of them trying to pretend not exist, so they can a little bit similar to the backgrounds. The first thing is that we utilize the instance-specific prompt to check whether the SAM has been given a point or Scrabble or bounding box from the ground truth, whether it can understand it. This three picture, the red part is the positive point, a blue part is the negative prompt. You can see red part, the positive prompt can be slightly different, but the segment result can be huge difference. That's because Sam do not understand what exactly is segment. This just depends on position of the prompt and the surrounding texture to make it predict. Even though it can make a seems like very sensible mask, but actually it's from time to time not appeal to our requirement. So in this case, we want to give a bounding box. We know bounding box provide much more information. Basically, it's providing more location information. So in this case, you can see the bounding box can get much more accurate mask result compared with the point because it provides more information as reasonable. But actually, from the last picture, you can see actually they do not know what's the meaning of the grasshopper. It just seems like, okay, this seems like we want to segment the grass. Here, most of them are grass. We just want to segment the shape similar to grass. So some parts of this do not segment pretty well. Another idea is Scrabble. It's just to provide proof that's our thought before. Even though Scrabble provides much more information about this one-to segment, actually sometimes the understanding between the human and the machine can be a little bit biased at the gap. The segment result still sometimes seems good, but not fit our requirement. And the final result is what we did by just provide, it's a camouflage animal detection task. So we just straightforward provide a camouflage animal. It's a task as a task generic prompt into 2 images and utilize our model to get a very good segmentation result. So how we do that? There's no magic here. Actually, we just borrow the idea from VLM. The key idea here is that given an image from X from a task set and the task generic prompt PX, for example, this can be the transparent object or maybe the shadow or just the camouflage animals, something. It's just about what task, what thing we want to segment in all the image within the task. And then our model, which is called Jian, trying to inference the instance-specific menu prompt, instance-specific prompt from the SAM, and to get rid of the instance-specific menu prompt, and see whether the segmentation result can be good. So we relax the requirement for each unlabeled image under the SAM text to have a unique supervision, and instead we adopt a common task generic prompt shared by different unlabeled images across data set within the SAM task. Here is one image. You can see the object we want to segment is totally different. The background are totally different. But we know in that tag, all these images are within the camouflage animal detection. So we just provide the task generic prompt, feed them, and we make this image, feed them together, and we can segment the result pretty well. So how we do that? Our idea is straightforward. We know that VLM have a very strong generalizability, so we utilize it to do our test time domain adaptation. Basic idea is all we have. We have generic prompt, we have a picture, and then we just do our called cross-modal chain of thought prompting. Firstly, we give an image caption based on Blip 2. Of course, here Blip 2 is just an example. We will transfer into Lava 1, Lava 1.5 to see whether it can be generalized to other models. And then, based on the caption and the image, we can straightforward utilize the chain of thought prompting to inference which animal in this image is related to this task. So that's what we did. But then we find out, because this task generic prompt is just a camouflage animal, it's very simple, it's very ambiguity. Sometimes we come to a very complex situation, this thing can be totally different. So we just want to see, maybe we can get some consensus from different perspectives. So we designed 3 different chains. For each chain, they just provide a slight different, but semantic closely prompt as different chains prompting. And to check what can be seen here. You can see in this here is grasshopper, maybe lizard, or maybe grasshopper. And then 3-4 ideas, we can make a consistency across different chains. But based on the self-consistent concept, self-consistent refers to in a closed set category list. We can see by majority voting which part is voting by most, which part can be the final result. But here the problem is we do not in advance what's the animal in that. We cannot prediction. But actually we are doing segmentation task. So in this case, no matter which kind of strengthening that, finally they will be transferred into the pixel. So we cannot do it on vocabulary level, but we can do it on pixel level. So we also provide a spatial clip. A sparse clip is a very straightforward attention strategy, which we influence the interesting object vocabulary into a heat map. It's just been proposed in the right. Here, this strategy is very similar to original QQV style attention, but the parallel line, we just provide another line which is called QQV. And so, in this case, both of them will encourage the model to pay much more attention to itself rather than the surrounding state, which can help it to get a better attention map even in complex situations. But sometimes we are talking about not only a straightforward or various object in a very plain background. Sometimes we are talking about complex situation, especially Sam cannot address. For example, the transparent object or shadows. In this case, the background and the foreground can maybe have very strong similarity, not only in texture, but also it's maybe in their colors. So in this case, detect the background is still very necessary for us. So based on this idea, we also utilize the chain of thought prompting strategy and to detect which object and what background in this image by its kind of cross-attention, by its cross-modal chain of thought prompting, and transfer the constitute by domain strategy on the background and the foreground. And on pixel level, we can just do subtraction to make the interesting object much more obvious. A straightforward idea for us, the first iteration may be not satisfied, so we can do iterative learning to make the object much more and more obvious. So we do it again, and again. And then we just utilize the result most close to the average to be the final result. The idea is pretty straightforward, and it can be easily applied because it do not need any labeling, it do not need any training data. So here is the result we do on camouflage object detection. The setting can be in three sets. First is called Scrabble supervision setting. Second is called point supervision setting. These two settings is we need the training set, but the training supervision level can be different. The Scrabble supervision means for each image you have to a specific Scrabble. Point for is much more less supervision, but at least for each instance, we interested have the 1 point as a supervision in the training. And our task generic prompt setting totally do not need any extra training set. Just one image, one task generic prompt, or a bunch of image within the task and the task generic prompt. We want to check whether the result can be good. Firstly, we do it on our baseline we have been proposed, and then we just say whether the other model combined with SAM can do pretty well, especially this model which SAM has been designed for open vocabulary segmentation or open vocabulary detection. So we compare our model which represents state-of-the-art method like the X decoder, SIM, grounding SAM, and our Jian SAM. Here is the strategy. We have just the transfer of baseline. Remember last year we have mentioned that baseline is split 2, and we just evaluate whether the different VLM can make the final result different. So we just replace the split 2 with level 1, level 1.5, and we replace the SAM with the SIM, and to see which result can be much more better. You can see from the result, our method can do pretty robust and compromising result compared with previous setting on the different model on the different setting. And you can notice that in some complex setting, our model can even do better than point supervision setting and get a very close or even a little bit stronger result compared with the Scrabble supervision setting. So another thing is that whether we can do it on other tasks, for example, on polyp image segmentation or transparent and shadow detection. We also doing this kind of experience on different sets, and you can see the result also very compromising. But sadly, on the transparent object and shadow detection, it cannot achieve the 100% the best result. That's because SAM itself do not have a strong ability to detect the background and the foreground when it have some complex background on the shadow on background. So here is some visualization of each iteration. You can see first the picture is image and it's gone through. This image and gone through. The final results is during our iteration, our heat map generated, and the gone through we have generated. You can see the result become better and better on the different during the training, during the test time adaptation, and also we provide some visualization of image in different tasks, including we mentioned the camouflage animal detection, also the polyp detection and transparent object and shadow. Also we provide some linear cases we have promoted. You can see our model can do pretty well on some people very complex task, especially on text and texture and the color. But for some shadow and transparent object, both our model and previous model do not pretty well and satisfy, especially when there's some overlap between different objects. And here is some demo we have provided. You can see during our optimization, the result become better and better. And finally, some evaluation study to check which model our hyperparameter and some pre-processing strategy, whether they work pretty well. If you're interested in our work, you can refer to our code link. We have provided our codes and our project detail in these parts. And so, in summary, what we are doing here today is just explore a very intuitive idea whether we can get rid of the inconsistency from the segmentation. And then we just prove that works, and we provide a baseline that can work on many different complex tasks. Okay, that's all.
We have time for one question. Any question?
So, how is this method compared with baselines in terms of inference time, computational cost?
Okay.
It looks like you need 5 times more computation than those baselines.
So basically, when we do comparisons for the clip surgeries, X decoder and both things, we have checked them by 1 time and 5 times. But we find out for these 3 tasks, when they do the iterative learning, their error will be accurate and the performance gets worse and worse. One of the reasons is that they do not have the ability to locate the thing close-defined. The first iterative, their object they have located can sometimes very bad. In this case, it's become worse and worse. So we have also, our later work also apply the baseline comparison of Lava 1.534 with SAM and GPT-4V with SAM to do a similar strategy based on our framework, and we observe the similar phenomena. So here we just provide the results. It's the best performance on this metric, but this not depends on which iterative learning or how many iterations it has been adaptation.
Thanks, Wu Jian.